This is section 7 now, circular motion. So first thing we want to do is picture a Ferris wheel. The cars on a Ferris wheel move in a vertical circle at a constant speed. All right, so assuming it's not speeding up or slowing down. So constant speed. Therefore, we can say that the cars are in a uniform circular motion. So when we're dealing with circular motion, we have uniform circular motion if we have a constant speed going around a circle. Okay, so that's a big deal, uniform circular motion. So, however, although the speed is constant as we move around the circle, the velocity is not, because the direction of the velocity vectors is always changing as we go around the circle, right? So we're going to draw a motion diagram, including the velocity vectors for one car of a Ferris wheel to kind of illustrate what that is talking about, okay? So let's say that we have a car on the Ferris wheel and it starts off right here, okay? And then a little while later, the car on the Ferris wheel is over here. And then a little while later, it's here. And then it's here. And then it's here. Okay, it's just moving around a circle. And it's here. And then it's here. And then it's here. And then here, right? So imagine that's like a perfect circle as this car on the Ferris wheel moves around, right? Okay, so then the velocity vectors would be drawn from each position directly over to the next position. Each position directly over to the next. Wow, I'm drawing real straight today. Each position over to the next position. Okay, that's our velocity vector. And we've talked about how it's the same as the position vector here on these motion diagrams. So these are our velocity vectors, right? So each one of these is a velocity vector. Okay, so now it says draw a motion diagram including velocity vectors for one car of the Ferris wheel as it rotates. So as it rotates around, it's going to come right back to where it started from, so that looks pretty good. Okay, now to find because the velocity of the car is changing, so right as we're moving around, we can see that the vectors as we move around are changing. Okay, so even though the car is rotating at the same speed the whole time in this uniform circular motion, the speed of the car is the same the whole time as it moves around the circle. The velocity is not the same as it moves around the circle. And because the velocity is changing, there must be an acceleration. Okay? If the velocity is changing, there must be an acceleration. That's what's being said right here. We know the car has an acceleration. Even though the speed is constant, the velocity is changing, so there must be an acceleration. Okay? Now, earlier in this chapter, we learned how to find the direction of the acceleration vector if we have the initial velocity and final velocity vectors. Okay? We can do that, just as a reminder, by taking the initial velocity vector. Okay, so let's say, I'm going to go back to the green color here. Let's say that this is the final velocity here, and this is the initial velocity here. Okay, so we have initial velocity, final velocity. What you do is you take the initial velocity vector and you reverse it, and you put it head to tail on the final velocity vector. Okay, so if I reverse this vector here, like that, and then I pick it up and I move it and I put it over here on the final velocity vector, and I set it down, the resultant thing now, if I add VF plus this negative VI, the resultant vector gives me the direction of the acceleration vector. Okay? So that would be my acceleration vector. All right? Now, if I did the same thing again, so this time, this is my V sub F, and this is my V sub I. So now I reverse the direction of my v sub I, and I place my v sub I vector here. I now have an acceleration vector, looks like that. Okay, if I continue working my way around, and I take my v sub I vector, and I reverse the direction of it, and I place it down, and I draw the resultant vector, I have my acceleration vector. Okay, if I continue working my way around, I'm going to have my acceleration vector looking like this every single time. Okay, so what's going on here? If you think back, we did a problem a while back that dealt with the skier coming down the hill, and as we were starting to go back up the hill, the acceleration vector was pointed upward. Remember that? The same thing is happening here. With the uniform circular motion, the acceleration vector is pointed like up the hill. Okay, so this is that we're going uphill around in a circle, and that acceleration vector is always pointed up, like directly up, right? So as we work our way around, the acceleration vector is almost like perpendicular to the circle. Okay, so what's happening is the acceleration vector is always pointed directly to the center of the circle. Okay, so it's a very interesting thing that happens here. The acceleration in a circular motion is always pointed directly at the center of the circle, always. So there you go. It's a very interesting thing. And the I don't remember in the notes. I think I probably have it in the notes here in a minute. But this is called centripetal acceleration. That is centripetal acceleration. The word centripetal means center seeking. So the acceleration is trying to pull the object that is moving in a circular path. It's trying to pull the object to the center of this circular path that it's on. That's what centripetal acceleration means. Okay, this is a confusing thing because if you were on that object that is moving in a circular motion, you're going to feel like you're being pushed outward, and we'll talk about that more later on. And people will say that's centrifugal. They'll use the word centrifugal, and that is actually false. That is not what's happening there. There is actually no such thing as centrifugal. Okay, it is centripetal acceleration that is pulling you in to the center. It's kind of opposite of what you think it is. All right, so centripetal acceleration is what we're dealing with here. Okay, let's move on. So no matter which point we selected in the motion diagram, we calculate the acceleration vector. It is always pointing to the center of the circle. This is the key result in uniform circular motion. That is centripetal acceleration. There it is right there. Acceleration that is always pointing to the center of the circle. And it's from the Greek root meaning center seeking. So there it was. I knew it was there. All right, so note, this is not a new type of acceleration. It is just a fancy name given to the acceleration of an object moving in a circular path. Okay? It is just acceleration. So the formula for centripetal acceleration, where the velocity is the speed of the object, or v equals the speed of the object, I should say, and r is the radius of the circle. Again, the arrow should be over the acceleration. I don't know why Cami is doing this, but it is. Acceleration equals v squared divided by r, where r is the radius, and that is toward the center of the circle. It is extremely important that you remember this. We're talking about an acceleration toward the center of the circle here. Okay? Note that this is a quadratic relationship, and that's because of this squared right here. Okay? A quadratic relationship means that if I have an acceleration, if I increase the velocity by a factor, then the acceleration will be increased as well by the square of that factor. Okay, that's an important concept to understand. So let's go ahead and go on. So we have short track speed skaters can cover the 500 meter of a race in 45 seconds. The most challenging elements of the race are the turns, which are very tight with a radius of approximately 11 meters. If you've ever watched speed skating, it's crazy how fast these people go around those corners. Estimate the magnitude of the skater's centripetal acceleration in a turn. So we just saw this formula here. I'll show it to you again. Acceleration equals v squared over r. And the acceleration is directed to the center of the circle, okay? A equals v squared over r. So we know we're probably going to be using that, right? A acceleration equals v squared over r. V is the speed of the thing as it moves around the circle, okay? So what do we do? Well, the first thing we need to do is probably figure out what we know and what we don't know. So we have the radius is approximately 11 meters. So that's a no-brainer. We have r. V is the speed. They gave us 500 meters. They gave us 45 seconds. So we probably need to calculate the speed using distance over time. Okay? So we can calculate V first. V equals distance, 500 meters, divided by time, 45 seconds. And that's going to give us meters per second. So 500 divided by 45, we're going to wind up with 11 meters per second. Significant figures. Okay, so now we can come up here. Acceleration equals v squared, so we have 11 meters per second squared divided by r, which is the radius, 11 meters. And if I do, I realize that 11 squared divided by 11 is just going to give me 11. And then the units here wind up being meters squared per second squared, but meters squared divided by meters is going to be just meters. So I have 11 meters per second squared. That's your acceleration. Okay? Toward the center. Acceleration is to the center of the circle. All right? Now the track itself is not a circle. It looks more like, that's a terrible drawing of a oval, but that's what it looks like. So the center of the circle that they're turning in is here, okay? So the acceleration would be directed to the center there. And then when they get on the straightaway section, there's no acceleration to the center anymore because they're going straight. And then when they get in this part, now they're accelerating to the center of that circle. All right, hopefully that made some sense based on my terrible drawing. Okay, so let's take a look at this problem. Which of the following particles has the greatest centripetal acceleration? So take a look at it, think about it. This is a conceptual situation. Come up with an answer. So we're looking for the greatest centripetal acceleration. Again, centripetal acceleration is v squared over r. So that means the bigger the velocity, the bigger the acceleration. And also because we're dividing by the radius, the smaller the radius, the bigger the acceleration. Okay? So those two things are going to combine. We need bigger speed, smaller radius. Okay? So just looking at the problem then, the biggest speeds are the 2v guys. The smallest radius is the 1r guys. Okay? So between D and E, just to look at stuff, between D and E is moving faster than D because it has 2v and the same radius. Okay? So it can't be D. Between A, B, and C, they all have the same radius. And because they all have the same radius, we're looking at which one is moving the fastest, because A and C both have the same V, and B has a faster V, 2V, instead of just 1V. B must be moving faster than A and C. Okay? So at this point now, we're down to just B or E. And because B has a smaller radius than E, and both B and E are moving the same speed, the answer must be B, because the smaller radius is going to give us a faster acceleration than the larger radius is. So that's why the answer is B, okay? Now you might have known that already, but I wanted to go through the process of elimination and show you why it must be B, okay? And believe it or not, that is the end of section 7. So you can now do those problems from section 7.